Hey, what's up, everybody? We have been talking a lot about different particles and their masses and various other kinds of energy scales in particle physics. And I realized that I've been introducing things in terms of electron volts, and I haven't really told you what an electron volt is or why we're using it or how you can relate it to something else that you know. So I thought I'd take the time to just describe very briefly what an electron volt is. Particles have masses, and those masses have weird units. But a lot of things in physics, science, and engineering, chemistry, whatever, have weird units. If you've taken a class, you're probably used to it. Frankly, unless you're in the weeds, day-to-day, hands-on with the data, performing measurements and doing analyses, units don't really have a large amount of meaning. I don't really care much about coulombs or farads or other units that electrical engineers probably care a great deal about. And I don't really have a good intuition for what they mean. Much in the same way, like a chemist will have something about moles, millimoles per kilogram or something crazy like that. I have zero intuition for that. The one thing I do have some intuition for, at least I'd like to think so, is electron volts. And that's because that's the unit that's typically associated with energy scales that we deal with in particle physics. But like I said, these are details, and for non-practitioners, we typically don't worry about them. But I wanted to give you some sense of scale, something that you could attach these masses of these particles with to your kind of everyday experience. Hopefully you've all heard of volts. Maybe you remember things like batteries back when we used to have to buy alkaline batteries back in the day, like a AA battery or a AAA battery. Those batteries are 1.5 volt batteries. That's how much kind of electrical energy they supply. Like we discussed, units are weird, and the volt is a really good example of a weird unit. It's kind of energy per unit electric charge. And engineers use it because that's just what's useful to them. It's kind of like measuring, population statistics when we talk about like number of cats per household or amount of rice consumption per capita. It's a number that has meaning relative to the amount of people or households or electric charges you are measuring it against. So when we talk about 1.5 volts, we'd have to first ask how many charges are we going to apply those volts to energize how many electric charges, and that will give us the total energy. Now, particle physics and electronics and electrical engineering and really quantum mechanics is a real big mess, and nothing is as simple as we make it out to be when we talk about it. But for our purposes here, we can really think about the electron volt as just one electron charge times a volt. If you imagine a perfect wire with just one electron inside, and we hooked that wire up to a AA battery, which supplies 1.5 volts, the amount of energy that we would impart on that one electron would be 1.5 electron volts. In other words, that's how much motion energy we're taking from the battery and pushing into the electron. But that's just one electron. That doesn't really make a whole lot of contact to numbers that you might be familiar with. Particle physics numbers like electron charge, things like that, they're just too small to be kind of intuitive for humans. Just for some perspective, the Large Hadron Collider at CERN has two particles coming at each other, both at 7 trillion electron volts, and the energy of 7 trillion electron volts is approximately equal to the kinetic energy, the 1/2 mv squared, of a mosquito flying. And that mosquito, of course, lands on your arm and barely deflects the hair as it lands, so it's really not that much energy altogether. Okay, great. So maybe we have an intuition for what an electron volt is, but that doesn't tell us why we measure masses of particles in terms of electron volts. Well, for that, we need to appeal to Einstein. Einstein's special theory of relativity tells us that mass and energy are related. Not only are they related, they are directly proportional to one another. E is equal to mc squared, at least for an object of mass m in its own rest frame. This is a different type of energy than we're used to thinking about. It's the energy that it takes to create a particle out of nothing. A great example of this happens when you have an electron and an anti-electron and they collide together to form a pair of photons. They annihilate, in other words. That energy associated to those masses gets converted into the energy of photons, energies in the electromagnetic field. And those energies of those photons are, again, exactly 0.511 MeV each. So put differently, nature can convert the energy associated to mass or matter into other kinds of things, which is nice because now we can understand how we can talk about particles like photons that don't have a mass, but do have energy. It's worth pointing out that this also works in reverse. So imagine, if you will, one of those photons was trapped inside of a box and that box was lined with mirrors. So inside the box, the photon bounces around with its energy, HF or 0.51 MeV. But from the perspective of somebody outside who is now trying to lift up that box, having captured that photon, that box now weighs incrementally more. Put differently, the mass of the box depends on the energy of all the stuff that's inside of it. And so it's affected additionally by gravity and so on. So, right, energy and mass are proportional to one another, and honestly, physicists just get tired of saying m divided by c squared, of mentioning that proportionality constant. So when you see somebody write the mass of a particle down in terms of electron volts, what they really mean to say is electron volts divided by c squared. In other words, it's implied, and the physics that's important to share with you is that energy and mass are directly proportional to each other. So that's all I really wanted to talk about in terms of electron volts, in terms of the units that we've been using to discuss particle masses. Hopefully that helped clarify things just a little bit. But anyway, thanks so much for watching. See you next time.